Picture this. You wake up tomorrow and every glass of water flows like syrup. Your heartbeat can't quite push blood to your fingertips, and the air in your lungs? It just stalls. Wild, right? But here's the kicker. According to a brand new physics study, that dystopian scene could have happened if the universe's fundamental constants had budged by the tiniest fraction of a percent. So today we're asking, how close did reality come to becoming a dead, sludgy cosmos? And what does that tell us about life, the universe, and, well, everything? First, a quick refresher. Physicists love to tweak numbers like the strength of gravity or the charge on an electron and see what changes. Up till now, the big question was, would stars or galaxies still form? That's cosmic, but a little distant from your daily life. Here's the twist. This new team zoomed way in. Instead of worrying about stars, they asked, could anything like a heartbeat, a neuron firing, or an oxygen-swapping lung ever work? To find out, they nudged several constants at once, just a hair, and fed those tweaks into computer models of fluid behavior. Not oceans, not rivers, fluids inside living cells. Think viscosity, surface tension, diffusion, the quiet background characters that keep every cell humming. Signpost, what happened when they pushed the numbers? At first, nothing dramatic. No Big Bang 2.0, no sudden cosmic freeze. Instead, the subtle stuff faltered. Circulation slowed, membranes leaked, chemical reactions lost their rhythm. Imagine a city where delivery trucks start arriving late while traffic lights go out of sync. The skyline is still there, but the logistics crumble. Same idea here. Biology's supply chain stalls. Now let's drill down. In the simulations, ATP, the cell's energy courier, showed up either too slowly to power molecular motors or so fast it shattered delicate structures. Membranes that normally balance perfectly between stiff and squishy became either leaky sieves or brittle glass. Enzyme networks, which usually dance on the edge of order and chaos, went one of two ways: frozen or frenzied. The takeaway? Coordinated biochemistry survived only inside a razor-thin, viscoelastic window. Step outside that window, and life's logistics unravel. But the researchers didn't stop at single cells. They scaled up to tissue-like flows. Picture capillaries. In one simulation, they clogged like rush-hour traffic. In another, they ran nearly empty. Pressure pulses that mimic heartbeats either fizzled out before reaching their destination or bounced back like destructive echoes in a pipe. Across scales, from nanometers to millimeters, the sweet spot stayed the same. That consistency is why the team talks about a web of constraints, not one magic number. Sure, you can tweak a membrane here or widen a channel there, but you run out of fixes fast. Too many interlocking requirements pile up, and the space for anything recognizable as biology shrinks to a narrow, winding corridor. Quick analogy time. Think of running a city where every subway train, traffic signal, and power grid is timed to the millisecond. Change the voltage by 2% or the train schedule by 3, and at first, life goes on. Give it a little more push, though, and commuters miss connections, warehouses overflow, and blackouts ripple block by block. That's our microscopic world, shockingly fragile, held together by tuned just right numbers. Two big implications jump out. First, even exotic life, say silicon cells swimming in methane, may still need its own tight viscoelastic window. Second, scientists now have a fresh way to test alternative universes. Don't just ask, could matter exist? Ask, could it stay organized long enough to do chemistry, to adapt, to evolve?
Where do we go from here? Cosmologists might treat the viscoelastic window like a boundary line on a giant phase diagram. Which universes keep their fluids inside it, and for how long? Astrobiologists can hunt for solvents that sneak into their own life-friendly corridor. And philosophers, oh, they get a juicy new puzzle. It's no longer just, why these constants? It's, why ones that let matter hold a beat for billions of years? Let that sink in for a second. Recap and takeaway. So, here's what we covered today. Rapid fire, but in plain English. 1. Tiny tweaks to the universe's fundamental constants don't first wreck stars, they wreck the quiet logistics of living matter: viscosity, diffusion, membrane stability. 2. Those logistics only work inside a razor-thin viscoelastic window. Step outside it, and cells freeze, fray, or fall apart. 3. The same narrow window shows up from single molecules all the way to tissue-scale flows, hinting at a deep, universal constraint. 4. This insight offers a new toolkit. Instead of asking where life could pop up, we ask where it can keep its rhythm long enough to thrive. 5. And beyond biology, it reframes the cosmic why, pointing us to constants that don't just allow matter, but let that matter stay in sync for eons. Here's the empowering part. The next time you take a breath or feel your pulse, remember, you're surfing an exquisitely tuned wave of physics. Everything from your blood flow to your synapses relies on that narrow window. Knowing this not only deepens our awe of the universe, it also sharpens our search for life beyond Earth. Thanks for listening. If you enjoyed this mind-bending detour through physics and biology, share the episode with a friend and keep the conversation rolling. Until next time, stay curious and appreciate that perfect, fragile rhythm keeping all of us alive.